So actually, don't expect anything too difficult from our talk for today. Actually, it's basic stuff. For some technologies like C++, maybe the topic will be covered in some deeper details because I have some. Most of my experience is C++ based technologies like C, C++, Rust. For other technologies like Go, C#, and other, I'm experienced much less, but I know at least something. And honestly, for other technologies except C, PGO is not great enough, at least for today. If you will have any question, just please try to remember a slide number on the right lower corner and ask your question, because you have really a lot of materials for today to cover. And we have some presents for the best questions. Actually, I am not sure that the best present is this one. Probably the best present will be a beer on us as a party. Okay, so let's begin. Nothing too difficult, but before we start, I will try to impress you and encourage to use PGO on the real software. And here we go. So I've performed a lot of benchmarks on the real software, like real, which I hope you use in your actual production environment, like databases, compilers, log solutions, network solutions like Envoy proxy, browsers, and so on. How many of you use at least one of these solutions in your production? Great, great. As you see, numbers are really impressive. At least for me, they are. So these benchmarks are not synthetic at all. These workloads are real, like Clang bench for databases, for log solutions, like parsing a lot of logs and so on. And let's begin. A few words about me. Name: used to be a C++ engineer for 5 or 7 years. I don't actually remember. I don't remember exact number. Now, for my skills a bit rusty. I was working on a C++ in the C++ committee and as an ISO standardization group. I was working, if you know something about C++, it was a study group about numerics, context stuff, and so on. Spent several years with hacking compilers, interpreters, and so on, static analysis. So I know something about compilers, not professionally, but something. Don't expect deep details about compilers, but at least I know people who knows a lot about compilers. And I spent last year and a half with optimizing different software with profile guide optimization on a daily basis. I optimized over 100 projects, something like that. And for my current job, actually nothing too interesting to speak about. So, before the start, some interactive glossary. Please, if you know the word on the slide, please raise your hand. If you don't know, don't hesitate at all. I will explain a bit in some details. Just for being in the same vein. How many of you at least heard once what is LLVM is? Okay, great. Actually, LLVM is not this abbreviation for low-level virtual machine. Actually, it's not at all a virtual machine. It's a bunch of tools for implementing compilers, static analysis, code formats, and different tools like that. I would say it's probably one of the most famous compiler framework nowadays, and many compilers modern, like for C++ Clang, for Rust, Rust-C, and for decompiler, are LLVM based. How many of you heard at least once at least one of this abbreviation. LBR, BRS, BRBE, or maybe CTR. Okay, that's completely fine. This some technologies for optimizing branch text sampling or BSS. This technology is used in Linux perf profiler. How many of you tried to use a Linux perf at least once? Great, at least several people, fine. We will cover these technologies a bit in details a bit later. And maybe someone heard about this technology, at least maybe by maybe in profiling tools like that. Anyone? Actually, this technology does not exist. It was a trap for you. So don't worry. Some proofs this does not exist. There are a lot of technologies, something like that, but not exactly. So, and AI proof, AI-based proof, as we like. So, why do we want more performance, actually? We like to optimize our performance, don't optimize and scale horizontally. Unfortunately, this way doesn't work in all situations, like startup time, serverless workloads, battery life for your favorite smartphone, limited amount of servers in your data center, or maybe some limitation on power supply with a real situation, trust me. Maybe reducing some total cost of ownership for your solutions, especially if you have a huge fleet of servers like Google, Netflix, something like that. Maybe special performance requirements for your context, like high-frequency trading or high-performance computing domain. And because we can, because it's fun, because why not? We can do it, we are engineers. So what do we do usually? Do nothing, because we don't care about performance in most situations. When we care, our usual path is run your favorite profiler, try to find the bottleneck, fix it, and continue this loop until we are satisfied with the performance for our application. Unfortunately, this way involves a human, and humans are actually quite expensive if we are talking about engineer salaries. And we have a lot of applications we need to optimize for our whole infrastructure. Maybe you will try to tweak your compiler somehow, maybe some different optimization level. I'm not talking about switching from debug to release. That's too obvious, like switching compiler options, like from 02 to 03, if we are talking about C compilers. Maybe trying to tweak compiler options in some deeper level, like try to apply several different combinations of compiler switches, because even an order of compiler optimizations influence on the performance of your application. That's how compilers work internally. Maybe trying to use CPU-specific, architecture-specific CPU instructions like vectorization stuff, SSE or AVX for x64 architecture, or maybe neon structures for ARM, and maybe enabling more tricky stuff like LTO, link time optimization. We will not cover this optimization in this talk, maybe next time, who knows. And actually, modern compilers are clever things. They do a lot of optimizations inside, like inlining, loop, roll and roll, devirtualization, and many other stuff. Don't think about this stuff in details. You need to know, for now, one thing. Almost all of these optimizations can benefit from knowing the actual runtime profile of your application, how your application is executed in runtime. And based on this information, a compiler can apply these optimizations much better, because inside every modern compiler there is an implicit model about how your application can be executed in runtime. And this implicit model doesn't work always in the best way in real world, because we have a lot of different workloads and so on. Actually, there are two different schools how can we implement a compiler. Just-in-time compiler or ahead of time. These are two different approaches. Just-in-time compiler work in this way. It compiles your code, source code for your application on a target machine, and then recompiles it if your just-in-time compiler is clever enough. Recompile it on demand, optionally optimize on the runtime profiler. For example, some examples of such just-in-time.
Yeah, there's an example in the C# when you build your code, compiler code as using mono scripting backend.
Yep.
It compiles in the JIT, which make it first launch of your application slower, but afterwards, after it compiles, it works pretty fine. Yeah. So this is the example.
Yeah. Another examples like V8, SpiderMonkey, or Chakra Core, JavaScript engines, your favorite Java compilers, for example, they by default are just-in-time compilers. Ahead of time approach has another way. It compiles your application once on a built machine, like on your favorite CI pipeline, like Jenkins or TeamCity, and this application needs to be deployed on all of your target machine, and this application is not modified on your target machines, usually. And here we see a huge limitation of ahead of time, lack of possibility to update, to adapt your application to a runtime profile. Just-in-time can, just-in-time approach can, ahead of time cannot. And actually, this is exactly the idea of profile-guided optimization. What if we will try somehow to collect a runtime profile for your application, then we try to pass this information to a compiler on your CI pipeline and use this information during a compilation phase. And in this way, we'll try to get the same approach as we have in the just-in-time world. This is all the idea, nothing more. Actually, profile-guided optimization has a lot of names, like a profile-guided optimization, feedback-directed optimization, and many others. A special one is profile-directed feedback, PGF. Don't try to Google it, trust me. And maybe a profile-online guided optimization, PGO. Sounds kind of funny. I will use only one, PGO, not PGO, because guided, like a GIF versus GIF. Sometimes feedback-directed optimization is used for some special kind of PGO, which is called sampling PGO. We'll cover this topic a bit later. So, actually, PGO has a lot of ways how it can be implemented, but two major ways are instrumentation mode and sampling mode. The most simple one is instrumentation mode. It will start from exactly this mode. So how instrumentation PGO works? You compile your application in the instrumentation mode, run the instrumented binary on your typical workload, in production or somewhere. We will discuss the topic a bit later. Collect PGO profiles, recompile your application once again, and that's it. You will get an optimized PGO application. That's all the idea. So, nothing too difficult. How does it work internally? Here we have an example of simple function in C++, like a meaning of life checker. We have only one input variable, and we compare with the meaning of life, 42. On the middle of the screen, we see an assembly view for this function in the release mode without any instrumentation. And nothing too difficult, actually. And on the right side, we see exactly the same code in release mode, but with the enabled instrumentation phase. We don't care at all about most of this assembly. The most important instruction is the first one, inc, quart, ptr, and some counter. This is how instrumentation works in practice. When your application is compiled with an instrumentation mode, your compiler implicitly inserts a lot of counters into any function of your application, into any branch of your application, and when your application is executed with a typical workload, these counters are incremented when your execution flows via different functions on branches. And then when your application is finished, all these counters from your applications are saved to a disk. Actually, they can be saved to a memory and sent to another server or something like that. But the most usual way is to save them to a file. And then this file is passed to a compiler. Some real example, like let's try to recompile Redis. I've tried this instruction on my local machine. They work, trust me. So just compile Redis in instrumentation mode. As you see here, we pass an additional flag, compiler flag, fprofile generate. This is an compiler switch for Clang or GCC compiler to enable a instrumentation phase for PGO. As you see, we also pass this flag to a linker, LD flags. We need to do it because instrumentation PGO requires some compiler runtime to be linked to your application. If you will not do it, you will get a lot of unresolved symbols, errors, and something like that from your linker. Run instrumented Redis server. Run your typical workload like Redis benchmark or your production, whatever you want. Convert PGO profile to a compiler compatible format. It's some limitation of the technology. And compile your Redis once again with profile information. That's it. Unfortunately, instrumentation PGO has a lot of limitations. And the first one, you need to compile your application at least twice. Once for instrumentation and another for optimization phases. Unfortunately, huge applications, especially C or C++, can take hours to build. And you double this instrumentation PGO, you double this time at least twice. It could be a problem, your CI pipeline will not be happy. As a second one, instrumented binary is larger because a lot of additional instructions are inserted into your binary. It can be a limitation, and the biggest caveat is the instrumented binary is slower. But how much? Actually, I collected several examples about binary size increase. For instrumentation PGO, I have much more examples, but I just decided to show some of them. Actually, as we see, nothing too critical here except envoy, because the size was increasing for time. But honestly, I think there's just a mistake in benchmarks in some scripts, build scripts, maybe release size for envoy was stripped from debug symbols, and the instrumented variant of envoy wasn't, because envoy build scripts are a mess, really, to tweak. So actually nothing too critical, but what about binary slowdown? And here is a problem, because we cannot actually predict how slow will be your binary in practice. Actually, you can try to evaluate how many branches are affected and so on, but actually it doesn't work in practice. The best idea just to perform benchmarks. You can wonder, is it a mistake or not? Is a ClickHouse like more than 300 times? It's not a mistake. I confirmed these numbers is Alexey Milovidov. How many of you knows who is it? Yep, that's an inventor of ClickHouse. And this is due to some implementation details of ClickHouse. ClickHouse has a lot of tight hot loops, and if these loops are affected with an additional counter, like during the instrumentation phase, the performance is affected a lot, as you see. And that's exactly what we got here. So actually, this problem, especially slowdown during the instrumentation phase, is well known. And Google is the largest PGO user in the world for now, decided to resolve it somehow. And the solution is sampling PGO. That's another approach to implement a PGO, which is implemented in all major C, C++, Rust compilers, and Go. Go actually implements only sampling PGO way. How does it work? Run your usual application without an additional recompilation, something like that. We don't need it. Collect a PGO profile in some special way. You can try to attach to your application an external profiler like Linux perf, Intel vtune, or whatever you want. Then you need to convert these profiles to a compiler-compatible way format once again, and recompile your application. And that's it. That's all the idea. Once again, let's try to recompile Redis, but this time with sampling PGO. Compile your usual Redis, almost usual. Here we see one additional compiler switch, gline tables only. Nothing critical, just insert some additional information about how your assembly code is mapped to a source code. It doesn't affect performance of your application, almost doesn't. Okay, it doesn't. Run Redis server under the Linux perf. You can choose actually any profiler, but Linux perf is the mostly used nowadays, and there is a tooling to convert profiles from Linux perf format to a compiler compatible format. Run your typical workload, convert PGO profiles via additional tooling we'll discuss a bit later, and that's it. And compile your Redis. Nothing interesting here, like an additional compiler switch if profile sample use. Exactly the same compiler switch as we had during the instrumentation phase, during the instrumentation PGO. And that's it. Unfortunately, sampling PGO also has some limitations. At first one, it's branch stack sampling support. This is a technology which helps to optimize stack sampling for your profiler. This technology is implemented directly in your CPU. This is a hardware feature, and it allows us to reduce profile collection overhead during a profile collection phase on your production, something like that. Unfortunately, support for this feature is kind of limited. At first one, for Intel CPUs, this feature is called LBR, or last branch record, and it was implemented many years ago in CPUs, and support also was added 10 or more than 10 years ago to Linux. I don't care about other platforms like Windows, macOS, FreeBSD, something like that, sorry. Regarding AMD CPUs, unfortunately, this technology, BRS or branch sampling, is available only since then free, and the support was added to a Linux kernel only 2 years ago. If we are talking about ARM CPUs, how many of you have ARM CPUs in production? Graviton CPU? Yep, it's obvious. For ARM CPUs, this technology is called BRBE, Branch Record Buffer Extension, and it's available only from the ARM from the last year, and unfortunately, as far as I know, this feature is not yet implemented in the Linux kernel. And if we are talking about more special CPUs like RISC-V, This feature is called CTR, Control Target Registry, Control Transfer Registry, sorry. Current status, work in progress, like a proposal, nothing more. And some more specific CPUs, like Elbrus or Long Soon that's Long Soon from China, like a MIPS-based CPU. As far as I know, in hardware, there is a support for LBR, but no support in Linux kernel, at least yet. And one of the most critical limitations here that sampling BSS doesn't work in virtual environments. So modern hypervisors like KVM or whatever VMware, as far as I know, they don't try to virtualize special registers which are used for BSS. So actually, you can use sampling PGO without BSS, but it will be less efficient. Not critical, but be aware about this detail. The second limitation is limited tooling support, because actually only Google cares about sampling PGO nowadays, and Google has some specific way how they implement different tooling. Google tools work great only internally at Google. And they don't care much about other world. They try, but actually not that hard as we want. For example, for native technologies like C, C++, Rust, Fortran, the only option to use sampling PGO is using a project which is called Google Auto FIDO. It's why FIDO is referred to as sampling PGO. This is exactly the reason. Unfortunately, Auto FIDO is buggy as hell. It can't be compiled, for example, with the latest compilers and so on. You need to patch it, you need to fix bugs. Of course, these bugs are reported to the upstream, but Google engineers don't care at all. Actually, if you have a C++ engineer, it wouldn't be a big problem to fix, but anyway. And there is another modern tool, which is called LLVM ProfGen. LLVM ProfGen is a part of LLVM framework. It works well. It doesn't have a lot of problems with compilation, bugs, and so on. But unfortunately, LLVM ProfGen doesn't work without BSS or LBR. This is a limitation. I, a few days ago, reported this limitation to the upstream, but of course we don't care. For a Go compiler uses another tooling which is called pprof. As far as I know, pprof is also developed by Google. I cannot say much about this implementation for some reason, which will be covered a bit later. But as far as I know, I played a bit with it. It works pretty well. And there is one more tricky thing. This is sampling PGO profile reproducibility. So for some environments, you want to implement reproducible builds. So you want to, every time you compile your application, your binary will be byte to byte equal to the previous one build. Sometimes you want to do it for the PGO profiles itself as well. For the instrumentation phase, it's possible to achieve with some caveats, but possible. For sampling PGO, it's actually not possible because we sample with some frequency. And frequency means time. And time is not so predictable, actually. And it could be a problem for some specific environments. So let's compare two different approaches. At first, instrumentation allows to achieve better optimization. How much? Actually, once again, according to Google measurements, sampling PGO has like from 80 to 90% efficiency of instrumentation PGO. That means if you want to achieve as much performance as possible, instrumentation PGO is your way. If you want to reduce runtime overhead for collecting PGO profiles, use sampling PGO. And you can, in situations, sacrifice several percent of performance. Sampling has far less runtime overhead, like 2%, up to 2%, and actually this 2% can be tweaked. For example, if you want less overhead, you choose you collect, you sample your application with less frequency. If you want to get more precise PGO profiles, you increase frequency, yes, overhead. It's tweakable. If we are talking about instrumentation mode, you cannot influence. Actually, you can, but it's not enough in real world. Instrumentation has far better tooling in general because this approach is implemented in many compilers, many modern compilers, and sampling PGO is implemented only in LLVM-based, GCC, Go, and Graal VM, but I'm not sure. And instrumentation has wider operating system support, once again, because sampling PGO for now works well only with Linux perf, and Linux perf obviously works only on a Linux. Go compiler hasn't such a limitation, but it's only Go. And instrumentation PGO has less problems with profile reproducibility, as we discussed earlier. So, common PGO traps. In some time PGO optimizes for one cases and pessimizes other cases. That's actually how PGO works in practice. How can you mitigate this limitation? At first, you can try to build several versions of your application per workload. And for example, if you are talking about web servers, try to build, for example, 2 versions of your web server and hide them behind the like a proxy and try to route your traffic based on some runtime feature, something like that, some runtime criteria. If it's not possible, actually, you can try to do another trick. You can try to collect as much as possible PGO profiles and try to merge them into one. And there's a huge probability it will work fine. Maybe not, you will not get a peak performance for each case, but in general, the performance improvement will be achieved. There are tools like LLVM Prof Data and others to do this stuff. PGO build is not reproducible. PGO build itself. The solution is simple. Just commit PGO profiles to a VCS and use this PGO profile during each compilation. And that's it. And the PGO profile reproducibility is actually another topic to discuss with some limitations, maybe after the talk. Not for now, we don't have enough time. PGO compatibility issues between architectures and operating systems. For each platform, you can have special code paths, for example, OS-specific code path, maybe CPU runtime dispatch based on CPU features like a different code path for x64 and ARM architectures. In this case, once again, generate PGO profiles for each platform, and that's it. PGO doesn't work for some specific targets, like WebAssembly. I'm talking right now about instrumentation PGO. Fortunately, this limitation hopefully will be resolved this year. LLVM engineers, at least they promised, try to invest resources into that. So let's pray. And in some cases, PGO cannot optimize your application. It's actually true for applications which are already heavily optimized, especially a lot of manually written assembly like a codecs, FFmpeg stuff or something like that. And in this case, will not be a huge reason to apply PGO, but maybe in a few years will appear in your code base some less optimized code, and maybe in a few years your application will be, your compiler will be able to optimize your software with PGO. So maybe if PGO doesn't work for now, just give it a try in a half a year or something like that. And there is a common problem with PGO, which is called PGO profile skew problem, because, for example, you collected PGO profile for your application and you committed it to your favorite VCS, but your application is not static. It's changed during the time. New code is added, the existing code is changed, and this new code is not covered is PGO profile. In this case, PGO profile will become less and less efficient. In this case, you need to regenerate PGO profiles each time or every week or something like that. You can decide your PGO profile regeneration strategy based on your context. Once again, it depends, because I'm an architect. And there are tools to help you to make some decision, like you can try to measure PGO profile similarity between different profiles and see some metrics like overlap between PGO profiles, and can decide about how frequently I need to regenerate my PGO profiles. So, how do I need to collect PGO profiles? There are different strategies, but at first, please don't collect from unit tests. Please know, there is obvious reason, but I need to explicitly say it. Unit tests have an aim to test your application in all cases, and most of these cases are corner cases, usually. But PGO does exactly the opposite thing. Try to optimize your application to a happy path from your actual production. So please don't do it. From benchmarks, like a Redis benchmark, as I've shown earlier, maybe yes. The actual question here, how well this benchmark represents your actual workload. In some cases, a benchmark like a ClickBench for OLAP workloads for databases is pretty good. Sometimes it's not. So it depends. From manually crafted training scenario, actually it's a good option. For example, when we'll try to optimize our compiler itself with PGO, the manually crafted scenario can be, let's try to collect PGO profile for a compiler from compiling a compiler itself. It's not a joke. That's how actually PGO for compilers is implemented for Clang or GCC already in production, or for Rust C. It's deployed for... How many of you have installed Rust C on your... It's a pity. So it's a real example. But be aware about one thing. Actually, your manually crafted training workload can become obsolete for the same reason as we had for a profile skew problem, because your actual production workload can change over the time, and you need to track it somehow. And collecting from production environment actually is the best option. Google collects all PGO profiles only from production. No manually crafted training scenario, something like that, only from production and only sampling PGO. That was exactly the reason why sampling PGO was implemented in Google. In this case, you will not have problems with profile skew, like obsolete training workload, something like that. The caveat, you cannot use instrumentation PGO in production. Actually, sometimes for some application you can. In general, you cannot. Because in general, you cannot sacrifice performance in production too much. But anyway, one answer, it depends. So, what about current PGO state across programming languages? C, C++, the majorest existing implementation in the world. Trust me, that's not because I used to be a C++ engineer. No. Fortunately, or unfortunately, Google invests a lot of money into C++ compilers because Google is the largest C++ user in the world, and they care about performance a lot because they have a lot of servers, really. So, Rust, D, and other LLVM-based compilers actually almost as C++, but some most advanced PGO features are not available yet, like a context-sensitive ER-based PGO. Don't think about it for now. Go, official compiler, actually it supports from, as far as I remember, version 1.20, like in the preview. Unfortunately, current Go compiler cannot do much with PGO. As far as I know, it can optimize only inlining decision and devirtualization with PGO, but once again, Google knows how to implement PGO in practice, and they invest a lot of resources into a Go compiler. So in a few years, I hope the implementation will be mature enough. C# supports. Unfortunately, I cannot say much because I'm not a C# engineer. This feature is called dynamic PGO. If you want to learn more, there is a guy, Yegor Bogatov. He knows a lot about it. GraalVM targets, like a Java, Kotlin, and other. It supports PGO, but unfortunately, there is no enough public available information about PGO efficiency. I asked a lot of questions in the upstream about GraalVM implementation, and one day they stopped to answer my questions for some reason. And other languages, with a huge probability, PGO will not be implemented, will not be available, because implementing PGO in a compiler is a tough task, really, and it's a difficult problem. So, what about good candidates for applying PGO? Actually, any software with a lot of branches inside, when like a lot of if statements and so on, like compilers, interpreters, databases, even operating systems and drivers, Linux kernel can be optimized with PGO right now. There are dedicated kernel build flags. And it's not the end. PGO can be improved. Current tooling, not so many tools for PGO are available on the market right now. In some areas, I could even say that PGO tooling sucks. So maybe will be a good idea to implement open source optimization platform, continuous optimization platform. So Google actually internally has a system which is called Google White Profiler, and based on this system, Google implemented a continuous PGO platform which optimizes continuously all Google servers with PGO. Unfortunately, there are no open source alternative for that. There are ideas to implement something like that based on Grafana Pyroscope or Elasticsearch Universal Profiling. Just an idea where currently we discuss with ideas with upstream. There are similar tools to a Google White Profiler like a Yandex Perforator. A perforator because it works based on Linux perf, and you know, when you run a Linux perf on many servers, it goes brrr. That's why perforator. But Yandex Perforator doesn't support continuous PGO optimizations for now. Maybe someday. So there are issues about PGO profiles interoperability, which can be resolved via additional tooling, and implemented more advanced PGO-related optimization, especially if we are talking about not so much implementations like Go. So happy end? Maybe yes, maybe no. Maybe rainy, maybe snow. So there are actually more advanced techniques which can be applied even after PGO. like a post-link optimization, LLVM bolt to improve code locality and with an idea to make your CPU instruction cache happier, some more advanced techniques and similar stuff like a Google Propeller. Application-specific operating systems, when you try to PGO optimize your operating system itself or interpreter specifically for your application. It's not a theoretical stuff. There are actual benchmarks for that. Machine learning-based compilers, also, it's not a joke. LLVM actually right now supports TensorFlow-based inlining engine, which tries to make inlining decision better with current implementation, and many other things we don't care about them for now. So maybe we can discuss after the talk, maybe next talk, who knows. So if you want to start with PGO, actually there is one of the best resources in the internet is my resource. For now, in this repository on GitHub, I've tried and I try to collect as much as possible information about PGO, like actual benchmarks, current implementation, different programming languages, documentations, collect PGO request issues into different projects, and many other things. Please start from this link and documentation for your and PGO-related documentation for your compiler. So, call for action: try to apply PGO in your environment, not directly on production for a start, maybe on your local host, test surveillance, and so on, whatever. Talk with upstream to enable PGO, for example, PostgreSQL developers, something like that. And spread the word about PGO if you had an success, like Datadog. Datadog tried to share the experience of PGO, Cloudflare, and so Cloudflare also uses PGO internally. And don't forget to have fun, actually. And if you want to share some results about PGO, please try to contact me via email, Telegram, Discord, and maybe here after the talk. And that's it for today. Questions?